Okay, thank you. You keep it here.
Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IIC. It is my pleasure to introduce today's speaker, Professor Sibiraj Pillai, the faculty at EE Department, IIT Bombay. He will be speaking on discrimination, a one-bit sampling perspective. Sibiraj Pillai is a faculty at ECE Department of IIT Bombay. He received PhD in Computer Science and Communications from EPFL Switzerland in 2007 and was a research fellow at University of Melbourne till 2009. His main research interest is in applying information theory to multi-user systems, feedback communications, and biological systems. He is also interested in radar signal processing, satellite navigation, and software radio prototyping of communication systems. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for more information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, please feel free to unmute yourself and ask directly or type them in the chat box and we will relay your questions. Over to you, Professor.
Yeah, thank you, Srinivas, for the introduction. Thank you, Parimal, for inviting. Thank you, Pillai and others for coming. It's a pleasure to meet you all. So, this is a little off topic for me also. This is not something that I work very regularly on. But then, as I said, there's some of these other topics that I'm interested in on communication and signal processing. Naturally, this is a derivative of those problems. So I picked up this problem from some real life situation and try to answer a little bit. There is no complete answer that I have at this moment, but at least I think people will get interested into this kind of problems. So this, this will work, right? Okay, I can drag it off or that top portion, or my title is getting a little, can I drag like that? No. That's okay. So the green allows me to drag a little bit. Fine. Okay. Okay, so what is being shown in this picture, at least as the motivation part of it, where I'm coming from to this problem, is in GPS and navigational systems, where we have quite a number of people at Bombay working on this, building Navig receivers from all the way down to the silicon chip. So here is some position where we have set the GPS receiving device to move. We can set any shape also. So this is somewhere around Pune, just for giving you a marker where these things are. We could do it right above IISc also, because these are all in our control, what to transmit and what to receive. So in GPS navigation, we have roughly 10 to 15 satellites visible at any point of time. 4 to 5 are enough to find where your position is. But nowadays, with GPS having so much there, a lot of satellites extra are available. And these satellites actually use the mechanism of CDMA. Each satellite uses a separate code to send data down to the Earth. And this receiver, like this trajectory that the receiver is taking here, he or she finds out what time transmissions occurred at different satellites and uses the time of arrival information to figure out how far it is from multiple satellites, and then uses the idea of triangulation to figure out what the exact position is. Nowadays, it's quite accurate. With 10 satellites, we can get sub 10 meters precision. Right. 4 is enough to kind of get a rough estimate, but we have much more. Not only that, our Apple devices or other things, they have even the good phones have not only GPS, but they also listen to Galileo, Baidu, GLONASS, In fact, some 30 satellites overall they can, and many a times they can even get to sub-meter precision also. Plus, they also suck into the network and use the network triangulation from the base station to identify your position in addition. So it's another fix. So overall, you fairly be assured that wherever you go, you are tracked by some intelligence agencies, for sure. Even if you get into some, like, you know, the Parimal's Munger, if you get into a tea shop there, Google finds it out and notes makes a mark and asks you a question actually if you want, how good is the tea? It does, okay, so it uses all this information out there. So this is essentially data coming from the satellites, and it is able to track all these things there. So this one, that the data is actually generated using a software radio receiver, which actually listens to the captured data and then reconstructs this waveform for us. And this is a very popular one. This is called GNSS-SDR. There is a free open source version running on my computer also. So what it does is that it collects data. If you have a satellite receiver, it can collect the data, or it can store the signal files, and then it does some conditioning, pre-processing to throw away unwanted data, smoothen filters and other front-end devices. And then the sample thing is sent through multiple stages of signal processing. And the signal processing starts with acquisition to say what the satellite, which satellite is present at this time, what is the time point where it is transferring, how fast it is moving. All those things are important to be captured. So the acquisition is a very, very time and computation intensive process. It will take a minute to 3 minutes to actually get the first fix on a GPS when you switch on. That's because this stage takes so much effort to find out all this data. Nowadays, we have made things faster by using the local connection to mobile towers and others to get quick corrections and things like that. So nowadays, people do this in 30 seconds or so, the first fix. And then the data, individual data, what was the time of our arrival, what is the satellite number, all this data will be decoded and then used for display like what I was showing. And that's called the navigational bits or the navigational data information available. So this is roughly how a software radio GPS receiver works. But the key to notice here is that the RF data sampled here are taken and almost like full precision. 32 bits is usually the processors that take it, that signal sample set. So both I and Q samples are taken and processed. It's quite intensive, and unfortunately it cannot be done in this very cheap devices, like 100 rupees GPS devices are available and very, very problematic for now. So if you look into the details, like some of these things, here is some correlation which is run to find for a particular satellite where the data starts, or where is the CDMA code starting point of that's called the code phase, and what is the speed, the Doppler at which satellite is moving. All this has to be in a crude way, like you have to brute force, you have to find those things out. Where are you starting in time, at what frequencies that you are moving, etc., etc. And then you get somewhere there's a peak, and then you identify that and say, now I know this much Doppler, that's the time at which things start. Right? And so this is a computation. And you can see that this all requires the full precision of data which is coming into the picture. So in this context, we ask this question. Suppose we take the data, but we only give you just a bit of that. We just give you the sign of the sample. Right? So no 32-bit precision, no floating points, nothing. Just give you the sign of the samples. And that is very viable for many commercial RX receivers that we build, including the one that is built at Bombay. It's 2-bit precision only available from this thing. So we don't have that luxury of real data coming into the picture. Just 1 bit of sample. How well can you do? Actually, I can do this program. I can run it right behind. I have to turn around and look, but let me just run this and show you. So I have put this thing here. So what I did was, okay, so it's not being shown. Oh, it's okay, don't worry. So I have actually put this data down to a local server. So this GPS information is now local host. At this port it is coming through. And if you watch out this place, that's the place where we were running the thing. So let me just run the program directly now and show you how it, maybe I'm overlapping a little bit with this one. Okay, so let me just. So I'm taking the samples, the signs of the samples, and running the entire software radio routine right on top. So now if you notice there, there's a web server here. I can make it a little bigger. So it's a real life calculation coming from just the signs of the samples, real data collected from a radio receiver. And if you look at that, just from that single sign of things, it is able to exactly trace through the path with almost no visible difference. It's like if 1 or 2 meters it will differ on that. So somehow this 1 bit information, that lot of 10 or 15 satellites, each of them superposed to give you the signal with different Dopplers, different time shifts, everything. But at the end of the day, just using that 1 bit of the sample, you are able to get it cleanly and actually track that GPS device right there. Right? So there is some magic which is residing in this 1 bit. Initially, we were not able to understand why this thing should work. But then a lot of commercial receivers only use 1 or 2 bits to do this kind of jobs. So can we make a better understanding of this? We are not near that, but that's where the problem started. I hope it's clear where we are trying to go. Okay. So 1 bit somehow miraculously seems to be enough, but the theory is far from complete on this story. So we were trying to fix this. Can we have a theory? Can we say when things will work, etc., etc. And then we looked around and found out that, oh, there are not much works on this kind of problems to say when you can decode with 1 bit or not. People have built things, made things working, but there is no theory outright available to explain this. So we started with the simplest of this thing. I hope it's not affecting the, no, it's not, okay, fine. Okay, so we went back from there and looked at the very basic, simple, primitive problem here, that there is a carrier cos 2 pi fc, there is a Doppler or an offset which is fd, so it's a simple cosine wave, there is a phase shift, and I should have put, there is a bracket also, here I missed the bracket, the weight, the noise term is actually adding the cosine term. And then we are taking the sine of that. So it's a plus or minus. Now can we use this from this? How are we going to track this offset here and this phase offset for this problem? If we can track this, then we at least have some understanding of how this more complex problem of CDMA can be done. So we searched around, can we get an understanding of this? So by the way, the sine is nothing but it's plus 1 if x greater than or equal to 0, minus 1, the usual sign of the number we are talking about. And our sample model is that we have the received signal is nothing but the samples of this. So we are taking, just denoting by n, with an appropriate number of samples per time period you can think, or per second you can think. Okay, this time I think I got the bracket correct. So I missed the bracket. Okay. Okay, and then what is the in phase component we are interested in is again the samples are down converted with 1 bit symbols from the local oscillator. So everything is 1 bit we are looking at. Receive samples 1 bit. So this is at the IF stage we are getting. That's why there is a FC. That's a carrier frequency percent. That's IF carrier frequency percent in the system. 1 bit from there. 1 bit from the local oscillator. That's a sign of a cosine term here. And we are taking a dot product of the samples, so n of them, and we are calling that as the in phase term. And this is how many of the receivers actually work on that GPS system that I'm trying. Everything is in 1 samples, like just 1 bits. Local oscillator 1 bit, incoming samples also 1 bit. Take a dot product like that, and then you have the in phase component given to you. That is correct. I is not 1 bit. Samples are coming at 1 bit, but you can accumulate the 1 bit. So it's a simple accumulation of that plus 1s and minus 1, and then you get an average of this number. So at this stage, we are feeding it to a processor who is able to handle it, a number as opposed to 1 bit. That's the question. It's clear, right? So we have 1 bits, but we accumulate to create a statistic which we think is sufficient. Let us see whether it's sufficient or not.
Your goal is to find FC and theta both?
Yes, our goal is FC is a non-component. FD and theta is the question that we are after. Okay, any other question? Because feel free to ask if there is anything which is unclear about it. Because I jumped from the more practical problem to kind of a theoretical model where we could at least see what's happening inside. Okay, similarly, there is from communication theorists will easily understand, there is a Q term also that you can use. There also we use a 1-bit local oscillator, and so it will be sine of another sine term, the orthogonal term, which we will take a dot product with to the same samples that we are talking. Okay. So from the I and Q, we are interested in figuring out that FD and theta. And since these are like square waveforms that we are talking about, because cosines, sine we are talking about, then of course we come to our 101 signal processing courses where we have such rectangles which have Fourier transforms as sinc terms. And square waves are nothing but repetition of this, so which means we get samples of the sinc function as a Fourier series representation, right? And for a equal duty cycle repetition, you will see that the odd harmonics are all 0, right? Only the even harmonics persist. And here there is a harmonic at 0 because we have a DC term. But if it's a centered square wave, then that DC term will also disappear. So you only have even harmonics present inside the system. So which means that our product, our accumulated metric, we can take a step back and think in the real time. Instead of samples, just think about, instead of summation, we are looking at the integration of this. And take this as our approximation to the in-phase term or the metric that we are computing. Right? This means that we have to sample at a sufficiently high rate, that's all. There's no other conditions that we have to put. So instead of summation, we have an integral and with the appropriate time given here. Now this sine cos is a square wave and which will have a Fourier series representation which we can put into. Yeah. So, sorry, certainly, that's a very nice point. If you, the existing implementations many a times do that very high order oversample. What we are trying to say is that you don't have to oversample by that much. Very small factor itself will be good enough for this thing to work. I'll give the numbers. My oversampling factor maybe is 1.4 or something. Still things work like the one that I showed you in the beginning. Whereas the actual ones, people talk about 20. And there it's clear that if you do sufficient oversampling, you can kind of get close to the Nyquist is no more, we are sampling it much higher than Nyquist, so we can very closely approximate the signal itself. That's correct. But we don't need that much is the story, the outcome of the story. Okay, so here is a square wave and we express it as sinusoids. And similarly, we can do with the R of t also, because that is another sine of a wave. So if we take the noise out of the equation, so the noise is absent, then this is a plain square wave also. So we can write it in terms of an appropriate frequency term, Fc plus Fd. This is only Fc. So we have two summation, one in M and other in K. Right, so we have two Fourier series, we have put them together. For the this approximation is because I took the noise to be 0 to get the exact square wave that we are talking about. Okay, so the question is that from this kind of metrics, can we find Fd and theta? Right, and that's the thing we are after. And there is some prior art, we kind of looked around, what is the answers, what are the answers people have given. So most of the works actually center around the case where Fd is 0. And we have to find a constant theta offset. And there are a series of works, patents and other things happening in the last decades, particularly relevant to navigation systems, GPS and others. Whereas as Phil pointed out, we can actually do higher oversampling by a factor of like 12 to 20 to get better reconstructions. In fact, you do oversampling and you kind of look at the zero crossings and then figure out the spectral domain properties of this thing. Very computationally intensive stuff, and these people have solved some of these problems there. And the actual practitioners are also they have also come up with lookup table implementation. You look at the I and Q that you get, and then if you see a certain I and Q, that corresponds to a certain frequency and theta. Right? So you have an entire lookup table kind of implementation. These are more computer scientists who have used this kind of stuff. So all this works, either they are looking only at the theta term, or they actually work on a very high oversample. Look at the details of where things jump, crossover from positive to negative and things like that. Okay, so that's where it stands when we started to analyze this problem further. Okay, any questions? Yeah, so theta and FD are the two terms we have to find from this. Okay. Let's first look at the case where this reference here is missing, but there is that work I was talking about where there is a constant phase. There is no carrier offset at all, but there is a constant phase offset. If there is no noise, the problem can be kind of simplified by looking at this case here, right? So here are the samples that we are getting, and we want to find where is the phase offset of them. So it's very clear that if you are right on top of each other, you get a very high correlation, and if you move out of it, then your correlation will decrease just like a triangle, right? So it's a linear function that will come out of this. That's very easy to show. And this reference, which is invisible there, shows that that's the answer they come up, and you get an answer like 1 minus 2 theta over pi. And then from there, from the I and Q, you can actually solve for theta, right? And this is something which was known in that works that I mentioned, like here. This case is here. Okay, so that's kind of turned out easy, but it becomes very difficult when you have a frequency offset there. So the constant phase offset, that there will be a triangle kind of thing. So I and Q will have this kind of a property. From there you can estimate theta very easily. And this is actually done, and that's part of the patent that I was mentioning earlier. Okay, so that's quite easy. But we can also take an alternate view from the theory that we were coming up with, the Fourier series based analysis. Can we recover this kind of result directly from there? And that will give us some good ideas of how to go forward. So again, this is the function that we are interested in, or this is a quantity that we receive, we measure, and we are interested in finding this FD and theta. From I, Q, you can use multiple I's and Q's to find it out also. Okay, so for FD equal to 0, if you look at this particular function, when FD is 0, then you have FC plus some term here, and there is a FC term here. So it's like cos A, cos B. And if you write in terms of A plus B and A minus B, then since there is no FC, only this extra term will come here. And so the whole thing will, along k equal to m, you will get a summation. Elsewhere, there is some term which will go down, or which has a term 1 by FC inside that. And the constant is a small constant only. So which means that the IF frequency typically is of the order of 5 megahertz, 2 megahertz, etc. So it's a very big term down there. So it's kind of negligible compared to the term. Right? If there is no noise, etc., this term does not, we can say that this will cancel each other out and it will become indeed 0. But otherwise, the dominant term is indeed of this form here. Right? Now we have to sit down and look at, oh, what is the Fourier series inversion of this particular sum is all we have to search. Turns out we are lucky, so this is, we can do the direct Fourier series evaluation. And because it's a continuous thing and using the uniqueness theorem, we know that indeed this is representing the continuous function which is mentioned here, which is same as the function the other people have already come up with. Yeah, so all these terms I am calculating, because when I wrote this term here, to get a square series expansion, I took the noise to be 0. If I put the noise, that square series expansion no more works, right? So to get some headway into the problem, that's the approach that has been followed by others also. Like, don't look at the noise. Can we say something out of that? Right. I will give you results for noise also as we go on. Okay, so that's lucky because we get the exact formula, and there are some terms which we have to carpet and throw it out, and that's sensible because FC is quite high indeed, megahertz. So whenever there is a FC term coming, and this integral, if it's on multiple of several such cycles, then you will see that terms will cancel and only 1 by FC terms will come. So having large frequency term in the integral is not good. The integral will take care. It's like a low pass filter. It will take care of all the high frequencies out. That's exactly what is happening on this picture. Okay. Now what happens if there is FD also into the picture? Then we cannot just subtract and write this term here because there's an FD term also. There is a phasor term inside that also coming into the picture. So they won't cancel each other. But can we handle that is the question. But if you look at that, there's a cos A cos B term, and if you integrate it, there will be a sine of term coming, and this term will also come on the bottom. So there will be K, M. So there will be 3 terms of K or M coming onto the bottom. The integral will push one of these K's below, the K is there, M is there. There will be 3 terms. So if you look at, to simplify, if you look at, let's say FD is not 0, but it is some very small constant times FC. Right? If you take, there is a very small constant times FC. Then the bottom term essentially is a sum of Km, K1 minus gamma minus M, where gamma is some small positive constant we are talking about. So when is this, what are the dominant terms of this, and when can we neglect some of these terms becomes the key question when there is this gamma, which is, if FD is 0, then gamma is also 0. Otherwise there is a gamma term coming here. So how to tackle this is the question. And we can actually look at the term where is 1 minus gamma times K is M, that's this red line which is shown here. If you are around that term, then this term is going to bite you because you are getting small on the denominator, so, and you have to sum up sufficiently high terms will come into the picture. But if you look at the level sets of the lines which are close to this line, so the blue line is actually touching the line 1 minus gamma K is equal to M. That these are the lines which will touch, and these are the lattice points because we have to count only on the odd numbers because the Fourier series coefficients, the even terms will all go to. So we only have to count on the odd lattice terms, K and M only need to be counted on that. So what we can say is that we can identify the level sets and say that anything which is far away from this or one step away from this blue line will bring in a non-zero difference here. And because of that, there will be an FC term coming into the picture, and so that terms will all go out of the picture. So we only need to worry about those points, these blue lines, where this function is can blow up actually, right? But when the blue line, this number here is very small, what happens is that this integral itself we can directly evaluate because of this difference being small, cos A minus B, that term will actually become very, very small for us to deal with. It's a constant term, and then the integral will average to 1, so we don't have to worry about that. That's the crux of the argument in solving this problem. So it turns out that you have to only worry about the blue lines, but the first time the blue line jumps to the another part is when the number is at least 1 by gamma, which means that the M or K has to be, the summation should be at least 1 over gamma or more before it jumps to the next line where K is not equal to M. So which means that if I just take the sum over all this K equal to M, it's as good an approximation, it doesn't change anything in the original problem. So what we can do is that if you take K equal to M, the integral becomes something of this form. Okay, so everything else in the picture is irrelevant because they all contribute much higher numbers. 1 over FC, 1 over the IF frequencies it will contribute, whereas the dominant term is only this much, but I add this term which is also a very small term to the whole picture to complete the summation, because completing the summation will allow Fourier series to again kick in and give us a very good answer to this problem. Right? Am I clear? Something missing? Please ask. Right? So we just summed over appropriate terms which will give us good numbers. All other terms we showed that they are irrelevant when there is a high IF frequency that we are dealing with. That's what we are trying. So now we have look at this term, sine of something divided by k cube, and fortunately that has a very nice Fourier series representation also. And it is this simple piecewise polynomial which will fit that Fourier series coefficient. Right? We can do a reverse evaluation and find out. Take this and evaluate the Fourier series, it will come out like that. Okay? So that identification makes things much more easier for us to solve the problem that we are after. Okay, so once we identify, then each summation here has an appropriate form like that. So our in-phase component is of the form, this is the function that I am representing here, f of nu plus theta, where nu is nothing but 2 pi f dt, where t is a non-integration period, fd is the only unknown part we are looking at. So if I know nu, I know fd also. So we can compute the difference of these two functions divided by 2 nu will give you the I component. So the in-phase component, after 1 bit sampling and integration, we were able to express this as a very, very simple, in terms of the difference of a very simple function. Simple in the sense of piecewise polynomial function. Any question? Some of the details perhaps are not exactly that important, but what is good is that that 1 bit accumulations end up with a very nice formula at the end of the day, and that this function is a function, it's a polynomial, piecewise polynomial function shown on this side. How does this function look like? Here is a plot of that approximation function that we are, in terms of nu, how is the function looking like, is this. And if you look at that function, first thing I kind of looked at it, it kind of, hey, why it's so much like a sine wave, so it should be a sine wave fitting on it, though it was a degree 2 polynomial piecewise that we were fitting. Turns out that is pi by 2 sine phi is a very, very close approximation. Right? We can bound the differences also, some 0.08 it or something like that is a maximal difference. So uniformly it clings onto the function all through the thing. So we can use either this function or the pi by 2 sine phi function in our calculations, and both works quite well that I'll show in the simulations. Okay? Okay, so let me now go. So now using this approximation, what is shown in this are the I and Q we plotted by using this function here. It's computed like that. And also the one generated and numerically computed by simulations. Right? So here are the values that I'm fixing at theta, which is a constant offset. And then this 1.1 megahertz is the IF carrier frequency, and 2.3 megahertz is the sampling frequency. So we are talking about a factor of some 1.3 or something like that. Okay? No, this is everything is 1 bit at the end of it. And the 1 bit simulation, but we numerically calculate the summation that we have to calculate, summation Rn sine cost of 2 pi fcn, and then exactly. Then we plot the formula that we have developed, and you can see that they very well match for both I and Q, saying that the approximation, the terms that we threw away really did not matter, even at a sampling rate of just 1.3 times extra. Not even that, right? This is FC, so we should not really count with FC, that the Nyquist rate is not coming from FC, but it's actual signal itself, right? So it's not, you can see it's, let's say roughly 2 point some samples per cycle of the IF that we are picking up. That's the numbers we are talking about. Right? Whereas the example implementation we have in our setup has, for the same kind of thing, you will have 32 MEC samples. 32 samples per FC cycle is what the implementations available become. Whereas this is much more lower than that. So there is a good agreement, and so that means the theory is clinging to the practical numbers that we are picking out. So we can use this to solve problems. Okay, and so first thing what we do is that we use this sinusoidal approximation, makes life easier. So if you substitute that in the approximate I component or in-phase component is a simple formula like that. Approximate Q component is a simple formula like that. But this is very easy because it's sin A plus B minus sin A kind of thing. So you can write it in terms of sums and differences, and very easy to calculate the phase. So if you take tan inverse of QA by IA, then you get nu by 2 plus theta. Nu is nothing but 2 pi ft t. So we can compute ft from this formula, and then we take one more measurement from 0 to t and t to 2t. Then you get another measurement. Solve the two, because from 1 you will only get the summation of the two. From the two you can solve for nu and theta, get the answer very easily out. Right? So the approximation in the end gives a very clean solution to the problem. So nu is that formula that is here. And this is called a tangent estimator, arctan estimator, and this is used in conventional communication system all the time. Q by I, tan inverse, and then difference will give you the frequency. Phase is identified this way, and this will give you the difference of the phase. We can do better actually. So what we've done here is that we have taken that I and Q, and we first normalized this by I plus Q, the summation of that. And then we try to do a linear fit. The formula will look like, or the functions will now look like that. And if you now try a linear fit, that's quite easy to get a linear fit on top of that. And using the two equations, you can again solve for nu and theta. So this is our second approach. First approach was using the sinusoidal approximation of the in-phase and the quadrature component. The second one was actually using a linear fit onto a normalized version of I and Q measurement. And here also you can see we have shown both the computed values and the simulations. And of course they agree very tightly to each other. So we can solve that one also using this I and Q approach. And we can also try what is called a numerical estimator, where we just take two consecutive instances and try to fit what nu and theta, because we know the actual formulas. We try to just see numerically which values fit that function. No approximations, nothing, just fit it directly. And that also gives a solution to this problem. So we have three solutions to that problem of finding the frequency offset and phase offset. And here is a plot which kinds of tells where they are. So the names are given here. This is a tangent based estimator, and this is the estimator using a linear fit, and this is the numerical solution that we are finding. As expected, yeah, when the SNRs, signal to noise ratios, are very high, so as if there is no noise in these conditions, you can think of here as no noise, then the actual numerical solution should work better, because that's the actual solution by our fits. So it gives a very good answer. And this linear fit based answer is slightly worse, whereas this conventional method is even poorer than that. Whereas if the noise gets bigger and bigger, that's the case where satellite communication really makes sense, is where the SNRs are actually low. So as you travel down here, then you can see this performance actually reverses. And subsequently we have made some analytical cut on that, what's happening inside. But then this all in terms of special functions, this, that, and all. No physical sense other than the special functions turn out to be better one way or the other. So I have not included those things here. But very interesting aspect also here, that if you look at this side of the picture, you see that as the SNR increases, this decoder performs poor. So that's a question one should think about. Can higher SNR make a decoder poor? Maybe you should make a guess. Can high SNR make a decoder poor? Except the professors, everyone else can answer. First we thought maybe we made a mistake in the simulations and things like that. But we went somewhat deeper to see the thing is, okay, so we have example systems where we can actually add noise and make the decoder work better. Right, because these are like 1-bit based systems, right? And suppose you have a decoder which some kind of a threshold decoder, and your signal is always below the threshold. But if there is a little bit of noise, what happens is that when you are near the signal, near the threshold, many of the noise realizations will take you above that. And using that, you can easily figure out, okay, that signal actually was a higher one or a lower one. So certain receivers actually can work better. Not the MLs and the optimal ones, where all these things are actually cleanly taken care of. But suboptimal decoders, sometimes noise addition can make things work better. This is one example. We have some more clear examples where we have made that. And these are like average performance over several frequencies and several theta's. It turns out when the frequencies are actually small, the performance is much better. Here, for example, the mean square error we are talking about is, or the absolute error we are talking about is roughly around a hertz. And so 250 hertz or 100 hertz, a hertz difference is not much. The next PLL stages will actually track that and correct all that things in our receivers. So that's good performance, but this is, though I have averaged all the performances, when the deviation is small, actually the performance is better. The error is very, very small, 0.0s, 0.1s, etc. But at 100 hertz, 200 hertz, etc., there are a few hertz of error that we make. That's pretty much what I had in this thing, because it's a work in progress. So so I kind of outlined what's the theory and practice behind phase and frequency discriminations from on-bit samples. Both local oscillator as well as the received samples are 1-bit quantized. Navigation, etc., it seems to be 1-bit is good enough. So I was hoping that we will have a better answer for that CDMAs and others, what is happening inside the system. Not so much, because we spend time on analyzing noise, etc. So unearthing the theory and performance limits of more practical systems will be of immense value, because then we can actually tell before somebody just builds a system, look, you need only 1-bit and so much sampling rate. Right now, it's a very conservative way of, you don't have too much sampling rates, but you build so much oversampling. As I was saying, 32 factor of oversampling is built into the systems that is developed for NAVIC reception in Bombay for that purpose. So once we know the theory and the performance, we can say, hey, don't do those kind of oversampling. Just 3 or 4 hour sampling should do a good enough job, right? And that is the story which is coming out, or the lesson which is coming out of this. And yeah, of course, joint work with Anil is my PhD student, Professor Appaiah is faculty, and Vivek is a master's student, just graduating. And, yeah, so that it took us some time to put together all this theory, and not only the theory, the complete show of putting it to a web server, moving it around the globe. And because the other application that I did not mention, that's a private one, is we can use this to spoof your GPS system. Like if you question, I will take it.
Thanks a lot, Professor, for an informative and interactive talk. Audience, please feel free to ask questions if there are any.
A lot of time. You think it's interesting?
Any more questions? So thanks a lot once again, Professor. So we have arranged refreshments at the coffee hut. So please feel free to continue your discussions if any. Thank you all and have a great evening.